Okay, so as I was saying before, so most of the time the difficulty is like trying to find the right perspective to use, and that's what we're going to be talking about today. And we're going to be like using some techniques that like are related to this idea of changing your perspective. Okay, so our first technique, or well, not really technique, it's an idea, is the bijection. So bijection, you can also call it a one-to-one correspondence. So, and the hint, and the name kind of hints at like what it is. Bi means two, so it's going to be a two-way like correspondence between like one thing and another thing. So if we have like a one-to-one correspondence between like some like counting A and counting B, then the number of A is equal to the number of B. So, and in like a visual sense, like so consider like this group of three dots here and this group of three dots here. So a one-to-one correspondence in like in between like these two groups of dots is like simply assigning one dot on the left side to another dot on the right side, and each dot on the right side has a unique dot it's assigned to on the left side, and each dot on the left side has a unique dot it's assigned to on the right side. So it could be something like this, or it could be like a bit more complicated, like this. These are all bijections. So does that make sense? Okay, I'll move on. And here's a kind of classical example of a bijection and how we can use it to like greatly simplify problem. So here's our first step here. After I'll give you a few seconds to read the problem before I go on. Okay, so our first step here is like say we choose the four digits that we know are going to be in the following number, like say like 7, 5, 2, 1. So say we already chose like 7, 5, 2, 1. Now how many ways are there to like arrange them into a following number? Like it's obviously one, right? You have to like order them from like greatest to least, right? So it's going to be one way. And okay, so here's the formal definition of a bijection. We have to determine if there's a if you can assign for each like thing in some group A, or like formally a set A, you can assign it to another thing in set B, and in set B you can assign it to another thing in set A. Because, and this is an equivalent to proving a bijection. You need this to prove a bijection, and it's like sufficient to prove a bijection. Okay, and now, so in a formal sense, A here is going to be the four digits. B is following numbers. So we've shown that like if we that for each 4 digits, like each group of 4 digits, it uniquely determines a following number. And for each following number, we obviously like can assign it to a group of 4 digits, like just the 4 digits that's like comprised of. So we have a bijection here actually. So yeah, and also uh, the 4 digits always form a valid 4 digits following number. We have to check for like the case if the leading digit is 0, but like this is not possible because then this implies because like it's strictly decreasing, so it's not, and because it's already first digit, you can't have like a digit less than 0, so it's not possible. Okay, and so our answer here is like 10 choose 4. Hopefully you guys like remember the choose function because we're going to be using it a ton here. Okay, here's our second example. I'll give you guys a few minutes to think about it. If you got the answer, you can just send it in the chat. Okay. So here's an example of like what. So I'm going to look at a smaller case here. Hold on. Yeah, okay. So here's like 5 points on a circle. And here's what it's going to be when all of the diagonals are drawn out here. Okay, so there's like there's five intersection points. Okay, and that's just an example to like give you an understanding of what we're counting actually. So we need to think about what makes up one of these intersections. So like a key idea when you're trying to find a bijection is you're trying to find what fundamentally makes up something. And you're trying to like basically break it down into these parts, and these parts are going to be kind of, well, they should be independent kind of in order for you to like easily count them. And so like in the previous example, we broke up a number into like its digits, and these digits are independent basically, other than the like condition that like they're distinct from each other. But like since the numbers themselves like don't really affect each other, we can like easily count them by just choosing any 4 of them. Okay, so in this problem we need to think about what makes up a intersection point, what defines an intersection point, and when we determine what defines it, we can form a bijection. Okay, so, and the hint kind of gives it away. So intersection point is the intersection of two segments, obviously. And what makes up these two segments? A segment's two endpoints. So we can think of a intersection point. So an intersection is defined by its two segments, and each of those segments are defined by two endpoints. So we can think of an intersection as being defined by 4 points, the 4 endpoints. And notice that when we determine four endpoints, the only possible pairing of these 4 endpoints into segments that gives a intersection is this one, obviously, because this or even this, they don't intersect inside the circle. So we have, so indeed, determining 4 points and not specifically the pairing still gives a bijection. Okay. So, and here's the key idea. Instead of counting intersection points, which we can't count directly because it's not intuitively obvious at first how we count intersection points, because there's a bunch of diagonals and they're intersecting in a bunch of different places. We instead biject and find something that we can easily count and show it's equivalent to counting the intersection points. And yeah, so, and the problem becomes much easier. Okay. Here's our third example. Oh, and in case you aren't familiar with the log expression here, so basically it's find the k such that n equals 2k to the power of k. Okay, so okay, so what's our first step here? So wait, actually I'm going to give you a example first of a possible grid, except we're going to be doing it a 5x4 because a 20x14 grid is way too big for me to draw. Okay, and a black square is going to be orange and a white square is going to be black. Yeah, so okay, so we need a even number of black squares, well, orange squares in each row and column. Okay, and here's a possible okay. Yeah, there's an even number of orange squares in each row and column now. This one has 0. orange which is even. And okay, so that's just an example of a grid, so you know what we're talking about here. So looking at the whole entire grid at once seems kind of overwhelming. So we look at a simpler case here. We look at like a single row of 1 by n. Because like 20 and 14, well, it's obviously random. They chose it to correspond to the year. In general, when you're doing like counting prompts and like they give you some random numbers that seem to be just like the year, you should try to like generalize. It's easier to think about the general case than it is for like this random case. And in the end, you can like apply what you know about the general case to this like specific case. Sometimes, uh, yeah. So sometimes in a general case, you actually need to. Well, actually, no. This isn't relevant for this problem here, but in a general case, sometimes you have to consider like the special properties of the number that you're examining, like the specific number. Like if it's odd or even or like 1 mod 4 or something like that, you have to kind of consider if like it can be any n. But like in this case, it can actually be any n. It doesn't have to be like odd or even. So we're good here. Okay, so anyways, back to the problem here. So if we're looking at a single row 1 by n, so what's the number of colorings we can do for this single row such that like the number of orange squares is even? So here's our motivating example. So say we chose a color for a coloring for the first n minus 1 squares and that we want even number of orange squares. So it's actually possible for all of the like colorings of the first n minus 1 square to like be extended into a full coloring of the n squares by, so like say there's like an odd number of orange squares here, then we just like make this orange. And if there's an odd number, we just like don't, if there's an even number of orange, we don't do anything. Right? And this is like the only possible coloring of the glass square that like works. Like for each of these cases. Okay, and to formalize our bijection, we need to show that like the two sets correspond to each other. Like one set goes to another set and the other set goes to the original set. So we've shown that like given an n minus 1 coloring of the a coloring of the first n minus 1 squares, we determine the whole entire row. And obviously when we determine the whole entire row, we also determine the coloring of the first n minus 1 squares. So we do have a bijection here. So we can actually expand this argument to the whole entire grid now. Okay, so and basically the idea is if we fill in this grid here, say this is like m by n. So if we cover any first, if we cover in this like rectangle here that's n minus 1 by n minus 1, we determine all of these other squares here. Like we determine this square and like these squares on the edge here. And there's kind of a special case here, like this corner square. is it true that like whenever we determine the first, so obviously this corner square is going to be determined somehow, but we don't know if we're going to like get a contradictory result from like going down here and going right, because like okay, so when we fill this in, we determine this square, and like all of these here, and we also determine these. So we have the first like n minus 1 and m minus 1 squares of the row and column. When we fill those in, when we try to apply like the technique that we talked about in the previous point, will we get the same like answer? Basically, will it tell us to like fill this in or like not fill this in for both of the like rows and column? So it turns out yes, you get the same answer from both the row and column, but you have to yeah, so you just consider it like the parity of this. So this is going to be same parity as this. This is going to be same parity as this. And by parity I mean like parity of the number of like orange squares. So what this means is in this row you have like the parity of like this whole entire thing here. Say A, this is like the sum of the parity of the sum of the orange squares here is going to be parity A, and this is also parity A because they're both the rectangle here, the sub-rectangle, and because these parities are the same here, they're going to tell this corner square to do the same thing. Does that make sense? Okay, good. Okay, and yeah, so we found a bijection is easier to count. Okay, now we're going on to complementary counting. Okay, so complementary counting is when instead of like counting something directly, you count the total number of occurrences and like the total number of like possibilities for something, and you subtract the number of the possibilities that like are bad, like, and which is called as complement with an E, not complement as in complimenting someone. Okay, and I think intuitively all of us have like done complementary counting before. If like you're good at school and you get high grades, then like on a quiz, if you got most of them right, like say 95%, in order to calculate the 95%, where do you count the number of questions that are right? No, you would like count the number of questions that are wrong and you subtract it from the total number of like points. Okay, and here's an actual example here. So how many of the base 10 numerals for positive integers less than or equal to 2017 contain the digit 0? So a easier question is actually how many of them do not contain the digit 0 like at all. It can't have the digit 0 in any of its decimal places. So this is actually a way easier question than it seems at first, because okay, our first step here is this is 2017, and so from 2000 to 2017 all of these must contain 0. So because like there's a 0 here and it's not going away anytime soon, so this is going to be 0. And for like the 4 digits, like what, well, we only have the like start with one stuff here. We have 9 to power 3 rays. For 3 digits, we have 9 to power 2, 3 again. 2 digits, we have 9 squared, 8 first 81. For 1 digit, we have 9. And we sum all of these up, which is, I believe, yeah, okay, so it's this number here, and we subtract 1548 from 2017 to get 469. Okay, that might not be correct because I'm bad at mental math, but you have the idea of complementary counting. So, okay, here's some exercises for you to do. I'll give you about like 5 minutes to do these 2 exercises because we're kind of like behind on time. Okay, moving on. Oh, I don't have solutions to these written up here. Okay, so I'll go over these very briefly. So we find a number of subsets that don't have any prime number at all. And so there's like, so these are prime numbers here. So there's 4 prime numbers and 4 non-prime numbers. So number of subsets that don't contain any prime number are 4 to the power 4, which is 2 to the power 4, which is 16. And the total number of subsets is 2 to the power 8, which is 256. So we have 240. How many and for a second one, how many 4-digit positive integers have at least one digit? That's 2 or 3. So complementary counting again. So there's 9,000 4-digit positive integers in total, and the number of positive integers that don't have a 2 or 3 in any of its like decimal places is 7 times 8 to the power 3, because there's 7 choices for the first digit. That's not like, it can't be 0, 1, or 0, 2, or 3. Can't be 2 or 3 here in any of these 3 places. And this is, you subtract and get, this is a 5. Okay, and now we're going on to like maybe the most important formula you need to memorize for counting and probability. This is like really common, so you need to definitely memorize this for contests. And so the motivation here is this one specific problem. So say we have indistinguishable balls. We would like to place these balls into bins called 1, 2, ... k. How many ways are there to do to like put these balls into these bins? So, and we need to have like a non-negative integer amount of balls, so we can't have like 0 balls in a bin. Okay, here's the solution to like this problem here. So we can, each of these asterisks here are like a ball. These represent a ball, and we have these k-1 dividers which separate the balls into k groups. Like this is the first bin, this is the second bin, and this is the fourth bin here. Third bin, fourth bin. So we can, okay, this is going back to the bijection subsection. It's the same idea basically. So we've kind of decomposed the grouping into its fundamental parts here, and by doing so we're able to like effectively count it, which is so like, because we have n balls here and we have k-1 dividers, there's like n plus k-1 choose k-1 ways to like arrange them, because remember the balls are indistinguishable, so like obviously the dividers are also indistinguishable. Yeah, so, and this is actually a very well known technique, and it's known by a variety of names. It's most commonly called stars and bars because these are stars and these are bars. And there's also sticks and stones and balls and urns. So, and also, another thing to keep in mind is that the number of dividers that you put in here is k minus 1, not k. And here's the formal statement of stars and bars. Oh, and here are some examples. Here's some exercises using stars and bars. I'll give you guys like 5 minutes again. Okay, actually, I'm going to uh, do like solve these a little bit earlier than 5 minutes because I realize we only have about 20 minutes left. Okay, so okay, so we can notice that okay, so actually I'm not entirely sure how this relates to stars and bars. So actually I'm going to skip it because because I don't think it's relevant for this section actually. Yeah, okay. So on the second one, so there's exactly so when we expand this out, this big expression, we get exactly 1001 terms that include all four variables to some positive power. So that means we need to have, so it means this does not count because it doesn't have any d here. So this is and this is actually stars and bars. Like say the powers are this. Actually, this should be, yeah. Okay, so we have w plus x plus y, and we can actually introduce a dummy variable here, like for a number of times you like do one. So, and this is a bit different from the stars and bars we did before, because these are positive integers. So the way we deal with positive integers instead of like non-negative integers is we can kind of algebraically we can just like subtract one from each of these variables and get like this here. And notice that the a doesn't have to be a positive integer, so we just like leave it alone. We don't subtract 4 from it. So we have, so when we subtract 1, before we had like w is greater than or equal to 1, w prime is greater than or equal to 0, which is the definition of a positive of a non-negative integer. So using this we can get, this is n choose 4, using these stars and bars we did before. And yeah, so we're given there's exactly 1001. Oh, hold on. Yeah, so we're given there's exactly 1001 terms, and we counted the number of terms here. There's n choose 4 terms. And if you memorize this kind of stuff, 1001 is 7 times 11 times 13. Yeah. And so using the algebraic formula for n choose 4, we get this. And we can actually rewrite this as this, and it's obvious now n equals 14. Okay, now we're going on to our final perspectives idea, the principle of inclusion exclusion. So the principle of inclusion exclusion is motivated by casework. Specifically, when we're doing casework, sometimes we can't like always guarantee the cases are like they don't have any overlap with each other. So in order to like simplify stuff, we have to like consider these cases with overlap. But like, how do you make sure you're only counting stuff one time if there's like overlap? So the principle of inclusion exclusion is like designed to deal with like these overlaps and basically allow you to like only count like each thing you want to count only once. Okay, and here's like some definitions to get you started with the formulas that we're going to present. These are, so this, actually I'm not sure how to pronounce it. I think, yeah, so these like bars around in set S is the number of elements in set S. And this is called the cardinality of set S. So like, say you have these 3 dots and cardinality is 3. The intersection of 2 sets is the set of elements that are in both sets, and it's denoted with a like this kind of N looking thing, a B. And for intersection, and the union of 2 sets is the set of elements that are in at least one of A and B. So this is A union B, and it's denoted with this U looking thing. So U for union and for intersection. And using this notation, oh, here's an exercise. It's kind of a prelude to the principle of inclusion and exclusion that we're going to fully go over. So A intersection B equals what? Okay, so we're trying to find this here. so A includes all of this and B includes all of this. So when we add up A and B, we get like, we count this once, we count the middle twice, and we count this also once. So, and notice that A union B counts all of this exactly one time. So when we subtract A union B, we get, yeah, so we get like the intersection here, because when we subtract, we only count like this once and the other stuff 0 times. Okay, and here's a kind of a application of this formula from a contest. Or actually, no, it's not from contest, it's way too simple. So, okay, so say this set here is like the set of people taking Spanish, and this set here is the set of people taking French. So, there's okay, X people here. So there's 20 minus X here, and it's 30 minus X here. We're given there's 45 people total, and when we sum this up, you get X equals 5. And the number of students that are only taking Spanish is 20 minus X, so it's 15. Yeah. So the principle of inclusion and exclusion is splitting the number. Okay, well, in terms of like the previous question that we're talking about, so consider if like there's more language classes, like say there's like Spanish, French, and German. How can we expand this kind of like argument to more classes? So, and is there like a general like formula we can use to find the union of the set, like the sets? So, there should be a bar here. Here's the formula for the two sets that we found before, and here's actually the formula for three sets, which is pretty much like the same idea. So we start. So okay, it's kind of messed up here, but basically you take the sum of all of the single sets, then you take the sum of all of the intersections of two sets, then you take the sum of the intersection of three sets. And in general, pi is, or pi is this formula here. So say we have like n sets, and we want to find the union. And notice, okay, this set notation might be kind of intimidating, but basically when you find the union of all of these sets, it's you can think of these sets as the cases we were talking about before, and when you find the union of these sets, you only count each thing exactly once, which is what we want, like in order to like prevent any overcounting. So it's going to be the union of all of these single sets minus not okay. It's the sum of all of these single sets minus the sum of all of the intersection of two sets. Then you add in the intersection of the three sets, and you go on like this, like until you reach n. And this kind of depends on okay, and so why is this useful exactly? It's because it's easier to count the intersection of two sets than the union of two sets. Cut in terms of like casework, because like if this is like a case here, like say if first digit's like 1, I guess, or and this is the case second digit is 2, it's easier to count the number of like numbers whose first digits like 1 and 2 than it is to count like the number of numbers whose like first digit who's like who meets at least one of these conditions, at least one. But like the intersection is both of these conditions at once, so you don't have any like ambiguity about like what the first two digits are. Whereas in like the union, you have to like basically you have like no idea what the first two digits are. And okay, and here's a example. Okay, and this is still a pretty basic pi problem. Okay, so say this is the set of car owners, motorcycle owners, and well, actually, nope. There's only two sets here. So this is the car owners and this is the motorcycle owners, and we're given the cardinality of set C is 331, the cardinality of set M is 45. So, and we're given the that C union M equals 351. So, applying pi, we have and we already know we already know 3 of these 4 terms, so we can solve for like the final final term. And this is 25 here. Any reason why, and then after we calculate the intersection, we can like calculate the number of what we want pretty easily. This is 306 because all of this is 331. Okay, and this is a bit more challenging. So 7 empty buckets are lined up. How many ways are to fill 3 of the buckets such that at least 2 of the buckets are adjacent? Okay, so So, say like buckets filled with water, like W1, W2, and W3. So we can construct three sets here. Three sets. W1 and W2 adjacent. And these are like these sets of like all the possible like arrange. Like these sets are like the elements of these sets are like good arrangements in which these conditions are true. So we want to find the union of these sets because at least one of these must be true in order for like the arrangement to be good. So this is pi. Yeah, so the and notice that like S1 is like by symmetry it's the same as S2 and S3, right? Because like we can just like swap around W1, W2, W3 to get like the same stuff, but for like a different pair. So we have that the cardinality of all of these sets are the same. Okay. And this is yeah. So there's 6 ways to choose where like W1, W2 can go, and then there's like 2 factorial ways to like permute these, like swap, like this can also be W2 and W1. And then there's like 5 ways to put W3 somewhere, which gives you 60. And then S1 union S2. This is all by symmetry, all of these are equivalent. So, so for S1 union, for S1 intersection S2, we can actually find that this is the only possible arrangement here. So there's like 5 of these. Okay. Yeah, and for like the intersection of all of them, there's zero arrangements that work because like so the intersection of all of them has to be some subset of the intersection of 2 of them, right? So like when we look at S1 intersection S2, there's no way these can ever be adjacent because they're like on opposite sides, right? So wait, actually, hold on. This should be 10 actually because we can also have W3, W1, W2. But the same idea of like these can never be adjacent still applies. So we use pi here and we get this. And then we have to divide by 6 because the water buckets are not actually distinguishable, because we assumed they were distinguishable here, and that's like okay, but we have to like account for it. Wait, so does that make sense to everyone here? This solution here actually might be easier because there's two sets. Instead of like looking at the water buckets like as distinguishable, like we kind of just access the set of like arrangements such that the like two leftmost buckets are adjacent, the and y is the set of arrangements such that the two rightmost are adjacent, which is okay. Yeah, this solution here is actually easier than the one I did before. Okay. Okay, I'm going to like just give a quick overview of these solutions to these because we're actually out of time. Okay, so this is the set for right-handed people here, R, and this is the set of people who are girls, G. So we have R union G. G is at most 30 people. We have R equals 22, G equals 14. And then we have, so using pi here, we have okay, and then we just do some algebra and we get the number of people who are girls and right-handed must be at least 6. Okay. In a higher secondary examination, 80% of the examinees have passed in English and 85% in mathematics, while 75% pass in both English and mathematics. So, okay. So call the number of the total number of candidates to be n. So, say this is the number of people who pass in English and this is the number of people who pass in mathematics. And 45 people passed in, 45 people failed in both of them. So, we're given these following numbers here. And we just like use stars and up. We just use a pi here to calculate the total number of candidates. Making sure we include this here, this 45. Which is, I believe, 18 annual return. Okay, so, and this gives n equals 450. Okay, and this is a free set Venn diagram. Shoot, this is actually very bad. Okay, we're given a ton of information about the intersection of these sets, and so we have four. So we have three people who are taking all of them. Oh wait, so call this Spanish, French, German. This is one because we're given this is 4 in total here. This is 2 because we're given 5 in total here. This is 4 because we're given 7 in total here, taking both German and Spanish. And then French. Actually, we can use pi directly here. Yeah, sorry. Using pi, we actually get this number here. This is the formula for free set pi directly, so I didn't. Yeah, so we should know the pi formula by like heart because it's really important for like casework. And that's the end of the lecture today. So, do you guys have any questions about what I talked about here? Okay, if not, I'll be ending the screen share and have a good weekend and a good Easter. Bye everyone.